Alright, this is the video for lesson 6.2, adding and subtracting vectors. So now we're going to take the idea of a vector and add them together. Okay. So any displacement AC can be represented by two or more displacement. Okay. So for example, if I want to get from A to C, right? Let's think about the shortcut problem. I can cut across. Let's pretend this is a corner lot. Or I can go from A to B and then B to C. Okay, so A is displaced to B under AB, and B is displaced to C under BC. The result is the same. You end up with AC, which is what we call our resultant vector. Since the image we see is a triangle, we call this the triangle law. Triangle law of vector addition. Okay, let A and B be two vectors arranged from head to tail. Okay, so A to B. So A, here's vector A. Here's vector B. The sum of A plus B is a vector from the tail of A to the head of B. Okay, so think of it this way. Think of it this way. We're starting here either way. So either you take vectors A and B, or you just take the shortcut, and that's our resultant vector. Vector A plus vector B. Okay. Now, what if I were to, so you can see here vector A plus vector B will give me vector A plus B. Now, what if I were given vectors A and B? So A vector A, there's vector B. Find A plus B and B plus A and prove that vector A plus B is the same as B plus A. Now, reading that, it sounds very intuitive, right? But our job is to show it visually. So we got vector A, which is red, okay? Vector B, which is blue. So A plus B, right? Now the arrowheads are important. Will give us the resulting purple vector, A plus B. Let's use yellow. Okay. Now, what if I were to go vector B plus A? Well, it's important because I'm starting with B now. So look at the blue. Okay, so vector B first plus vector A. Okay, but we still get the same resultant vector, the same purple vector. Now this is called the commutative law of addition. Okay. Now what about subtracting vectors? Well, to subtract vectors, what we need to remember is vector A is the same as negative. Okay, remember opposite vectors. Okay. So, what if vector A was added to negative A? Well, we call this the zero vector, back to where you started. So vector A, so let's pretend this is vector A. Okay, then what is negative vector A? Well, negative vector A is just the same vector, so overlapping it, but going in the other direction. So don't you just end up where you started? That gives us the zero vector. Zero vectors have no specific direction and zero length. Since, whoops, since, sorry, 1 second here. Okay. So since the zero vector has no value, the scalar value of a zero vector is 0. But to be cleared, this is not the same. And why? Because this is a zero vector, and this is a zero, like the number, meaning nothing, right? So these are not the same, just to be clear, because a vector and a scalar will never be the same. So what's the parallelogram law of vector addition? Two or more forces or vectors act on one object so they can be arranged from tail to tail. Okay? In these cases, we can graphically complete the parallelogram formed by the two vectors and the resultant vector from the tails of A and B to the opposite vertex of the parallelogram. Okay, so what does that mean? Well, let's think about this. I'm going to redraw this to kind of clarify things. So if you've got A, then this is what we just learned, plus B, the resultant vector is vector A plus vector B, right? Now think about what we learned in our last lesson, or 6.1, about equivalent vectors. This vector here, right, will be the same as this vector down here, forming a parallelogram, right? So what this is stating is, and this will always be the case, is that vector A and B, if I were to draw them out, vector A and vector B, if I were to add these two vectors together, and I notice how in both cases it's tail, we start at the tail to the head, tail to the head, the resultant vector will be in the middle, forming our parallelogram. Okay? So let's take a look at how this works. A boat with a velocity of 14 meters per second due north, so that's this first line here, is traveling across the river with a current of 5 meters per second due east, which means there's a current that's pushing the boat this way, to east, to the right. Find the resultant velocity of the boat. So the resultant velocity of the boat will be the purple line. Okay, so from tail to head. Now, how would we solve this? Using Pythagorean's theorem. 14 squared plus 5 squared equals c squared. Solving for c gives you 14.87. Okay, that's great. That's the magnitude. But we need to be able to find the direction, which we don't have right now. We can use trig. So tan of theta is opposite over adjacent, so 5 over 14. Solve for theta, giving us 20 degrees. Okay, so now the boat is traveling 14.87 meters per second due north, but 20 degrees east, and that's because of the current. So if I wanted to look at this question another way, which I wouldn't in this case because this made sense, right? But there will be questions later where lining up the vectors tail to tail might help. So for example, for this one, I could have done 14 meters per second, and then the current, so tail to tail, 5 meters per second. Okay. And then this clearly forms a rectangle, right? If I were to draw the equivalent vectors. So the resultant vector will still be in the middle. Yeah, will still be that one right there, which will be the resultant vector of the boat plus the resultant vector of the, the vector of the speed of the boat plus the vector of the current. Okay, vector subtraction. Just as scalar subtraction is the opposite operation for scalar addition, this just means subtracting is the opposite of adding, right? Vector subtraction is defined as the opposite of vector addition. So, in other words, vector A minus vector B is a vector that must be subtracted to B, added to B in order to obtain A, where A is OA, B is OB, and A minus B is B to A. Okay, so here we have vector B and vector A. Okay, so we got two vectors tail to tail. Now, so we're looking at vector A. Let me just try to see if I can fit all this in the same screen. Note that two vectors A and B are arranged from tail to tail. A minus B is from the head of B to the head of A. Well, why does that make sense? Well, vector A minus B, right, means, so if I'm starting here, okay, and I'm going to A, I'm starting here, I'm going to B, what do I need to add in order to end up where I started, which is that resultant vector, okay? It's essentially eliminating the vector B, okay? So using the triangle law, okay, so if I wanted to, because I want to end up where I started, right? We can also use the triangle law to show that vector BA is the same as BO plus OA. The one thing to remember is head to head, okay? So you're looking at A subtracting B, because if you wanted to show this with addition, you could, right? Because let's pretend that this is, let's backtrack a little bit here. What does negative vector B look like? Well, vector B looks like that, which means negative vector B is just the same magnitude but facing the opposite direction, right? So now, if I wanted to add those two together, so vector A plus negative vector B, so that's vector A plus negative vector B, well, using vector addition, which is what we learned before, you get from tail to head A plus negative B. Well, is this not the same vector as the one we see here? Okay. So there's two ways you can look at it. When you're subtracting vectors, you're really just adding the negative version of it. So for example, using scalar values, 5 minus 2 is 3, right? Or you can say 5 plus negative 2 is still 3. Okay, so essentially that's what we're doing when we're subtracting vectors. But what ends up happening is it ends up being the head to head, because the reasoning is if you're starting at A, you're looking at vector A, okay, and you're subtracting B or adding negative B, what you're trying to do is, so since this B vector is there, you're trying to remove that vector B, so negate it, right? Which means that in order to negate it, you need to add this vector to bring it back to just vector A, okay, which means that green vector I just drew represents vector A minus vector B. Okay, last example. Express each as a single vector. So vector CD minus CB. Well, CD, where's CD? Vector CD is right here. C to D. Okay. Minus vector CB. Where's CB? CB. Yeah. So CD minus CB, which means that if you look back up, CD minus CB, or vector A minus vector B, from the head of B to the head of A, because you're going back to where you started. Okay? So CD minus CB, so CD, and here's CB, which means that this vector here, going back to where you started, represents the vector CD minus CB, giving you vector BD. Okay. Or we can look at it that way, or we can look at it as we're adding the negative vector of CB, right? Going back to this example. So vector CD plus the negative vector of CB. So let me just erase this and clear this up a little bit. Okay, so vector CD, which again is right there, okay, plus negative CB. Well, where's CB? So CB is right there. CB, let's use, that's CB, but we're looking at adding the negative version of it, right? So negative version of CB, which means it's just going to be BC then. Okay, BC. Well, then going back to vector addition, okay, so I'm going to use blue. So if you start from B to C, C to D, well, what's our resultant vector? BD. Again, same answer. Okay. All right. Any questions? Feel free to shoot me an email. Yeah, we'll talk soon.